So we have seen that for a series resistance, equivalent resistance is just the direct sum of all the resistances R1 plus R2 and so on up to Rn. So this is the case where we have resistances in series. Now let us see what will happen in case of parallel resistors. In parallel resistors, this is resistance R1 and this was the resistance R2. Both these resistances are in parallel. So the potential at the ends of these resistor or potential drop was same. There was same potential drop. What happened? The current I started from this point and it divided into two parts, I1 and I2. And after getting out of these resistor, this current again combines and form the current I, which was same as before. So this is the case when we have resistances in parallel. Potential at the ends remain same while current divides into two parts if there are two resistors. So let us take the case of two resistors. Resistors be R1 and R2. The currents are I, that is total current, I1 and I2. So that was shown in this figure. So we know that total current remains same, I is equal to I1 plus I2. Now the potential difference again remains same. We know that potential difference along both the conductors was same, both the resistors was same. So let's write this equation. Potential difference is equal to, from Ohm's law, V is equal to IR. So for first resistor, current is I1, resistance was R1. Now for second conductor or second resistor, a conductor is also a resistor because it behaves as a resistance in the path of a current. Though resistance is quite low, but a conductor is also a resistor. So I2, R2. So these are two equations. Both are equal, both have equal potential. Now let us combine this. So from this I1 is equal to V upon R1 and I2 is equal to V upon R2. So we have these two equations. I1 is equal to V upon R1 and I2 is equal to V upon R2. Now we know I is equal to I1 plus I2, sum of both the currents. Now putting the values, I1 is equal to V upon R1 and I2 is equal to V upon R2. So let us take V common, 1 upon R1 plus 1 upon R2. Now I is equal to, so V is equal to I total current, and let us replace this total or both the resistances with an equivalent resistance R equivalent. So V is equal to I R equivalent. We have replaced that parallel resistance with some equivalent resistance R eq. So in that case, I is equal to V upon R eq. So that is, so same thing, I is equal to V upon R eq. So we have now two equations. I is equal to V upon R eq. I is equal to V 1 by R1 plus R2. So equating both of these. So what happened? V gets cancelled out. What we get? 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. So let us see. So this is the equivalent resistance. 1 upon R eq from this is equal to, this V cancels out, 1 upon R1 plus 1 upon R2. So I prefer the words RS, that means series, and RP instead of R equivalent because it is confusing. So what we had, RS was R1 plus R2 and so on. What was RP? So for RP, 1 upon RP is equal to 1 upon R1 plus 1 upon R2 and so on. So here we can see that for parallel, resistances are added in inverse. For normal series resistances are directly added together. Now let us take a case where we have added one more resistor in parallel. So now R1, R2 and R3, and the currents are now divided in I1, I2 and I3. Starting current is same I, ending current out is also same, and the potential difference at the ends of all the resistors is also V same. But what happened, we have added one more resistor, hence current I3 is also there. Similarly, as previously, the current I is equal to I1 plus I2 plus I3, and potential difference is same, V is equal to I1 R1, I2 R2, I3 R3. When taking from this equation, value of I1, I2, I3, V 1 upon R1 plus 1 upon R2 plus 1 upon R3, and I is equal to V upon R equivalent, again cancelling out. So R equivalent is 1 upon R1 plus 1 upon R2 plus 1 upon R3. Similarly, we can extend up to 1 upon Rn. So this is for parallel case. So this is the formula for parallel. I always prefer the word Rp and Rs, so we can have a much more clear differentiation. So these are the formulae for equivalent resistances, can be used to find out the current and voltages in more complicated circuits. So if we have more complicated circuits, we can use there as well. Now let us remind us some important difference. So Rs series resistance was R1 plus R2 plus R3 or and so on. But when we had in capacitances, so what happened in case of series capacitance? Series capacitance was 1 upon C1 plus 1 upon C2 and so on. Capacitance and resistances are opposite of each other. Similarly, resistance in parallel case, resistance is 1 upon R1 plus 1 upon R2 and so on. So this is in case of resistance. What happens in case of parallel capacitance? Parallel capacitance was simply C1 plus C2 and so on. So again, these resistances and capacitance are opposite. So you remember this thing that for resistances add directly in series while capacitances add directly in parallel. So this is a point to remember. Now let us solve a little bit more complicated circuit. So in this circuit, the circuit is little bit complicated. Again we have 2 points A and B which are end points, and there are 2 resistances. This resistance R1 and 3 resistances, not 2. So this R2 and R3. These resistances R2 and R3 are in parallel, and this resistance is in series of these resistance. So what we can do? So first we can calculate R parallel for these resistances, and then we add simply this R1 and Rp to make a equivalent series resistance. So what we did, Rp, first we will calculate this Rp, then we add this Rp and R1 to make the total series resistance. So let us calculate what is this Rp. Rp, they have shown Rp by R equivalent 2 and 3. So R equivalent 2, 3 is 1 upon R2 plus 1 upon R3. Same here, 1 upon Rp is equal to 1 upon R2 plus 1 upon R3. So this is Rp, parallel resistance. So this equivalent resistance, let us take common. So R2 and R3 is common. So R2, R3 is in denominator, and R3 plus R2. R3 plus R2. So this is 1 upon Rp. So when we again take Rp, Rp is equal to this goes into numerator and this goes into denominator, R2 R3 upon R2 plus R3. So this is the equivalent resistance of this one. Now what is the total equivalent resistance? So total equivalent resistance of 1, 2 and 3, all of them, is this R1 plus this R equivalent. So R equivalent plus R1. So again the current flowing is total potential upon total equivalent resistance, that means equivalent resistance of 1, 2 and 3. So now what is that? V is the potential drop, and what is this R equivalent? R1, from this R1, and this R equivalent 2, 3 is R2 R3 upon R2 plus R3. So this is I is simply, let us take this into numerator, this is V R2 plus R3 upon, when we take this common, this will become R1 R2 plus R1 R3 plus R2 R3. So this is the current flowing in this circuit.